Okay, today we're going to be working on Department 56. God, I forgot the name of it. Today we're going to be working on Department 56's Doctors Lunatics Laboratory. This is a common one that fails, and that's because it's a 3-volt piece and people plug in 4, 5, 12-volt adapters into it, and well, they have a tendency of not liking that a lot and smoking. So I had one sent in to me, and it needs to be repaired. And then I have my own that needs to be repaired. I bought it the same way. So in the interest of time, I'm going to switch out this one for the other one I've already taken apart. How you do it is here we go. Watch magic. Look at that. So they both need to be fixed. They'll both be fixed the same exact way. But I already heated this one up, popped the dome, because you need to come in from the top. And then I pulled the coil of wires up. These are just shoved straight down inside. They just hang. Now you might be able to tell this one, I think, had a 12-volt adapter plugged into it. I'm going to zoom in to show you what happens when you put too much power to these things. See how the wires are nice and shiny? They're all loomed, bundled together for the different colors that you see in here. You got orange, red, and yellow. And do you notice this guy right here is kind of black? Yeah, that got really hot. So that's kind of tough on the unit. What controls this is 2 light patterning circuit boards. There's one here. Oh, I forgot I zoomed in. And there's one there. So here's the one, and there's the other. If you watch the... oops, wrong direction. There we go. Octo swing, where I redid the lighting on it. I use a timer chip versus the transistors. This one will probably do the diode chip, or excuse me, the IC chip again versus the transistors. Probably just because of its longevity, and I can control how fast it flashes a little easier. But this uses a standard lighting circuit, which even Lemax uses, where they use multiple transistors and resistors to make them flash. They go on, off, on, off, on, off. Basically, they're just on-off switches. And this uses 2 sets, because there's 3 colors in the top, and then there's 1 in the bottom. So, in the top, we have the red, orange, yellow, plus up there is the same. It's orange, I believe. But down here is blue. Blue runs at a different voltage. So, they have the main power, which is these 2 black wires right here, coming into this board, which then branches off to this board, which then goes down to these lights down here. None of these lights work with the standard 3-volt power supply. This does put out floating, no load, 5 volts. It is a working power supply. Same with the other one. They're both fried. It happens. A lot, actually. So we are going to make sure that all the lights work, which they should, because usually the LEDs don't get damaged. Keyword being usually, because on like the Octo Swing, 60% of the LEDs got fried when it was overpowered. Oh. Now these wires, even though they all look bare, they're actually varnished, or they've got a very thin clear coat on them to keep them from shorting out against the other looms. Each loom itself doesn't matter, because if this loom shorts out to itself, it's the same leg of the same lights. So we need to separate these and figure out which are the hots, which should be these 3, which means that these are the nots, or the negatives. And how you test it is if you have a power supply. We know that this is a 3-volt house, which means everything in here is going to run at or below 3 volts, hence the resistors that are right here. So I'm going to set my machine here for 2.2 volts, which is a very common voltage for low-powered LEDs, such as reds, oranges, and yellows. And I want to test them. So let's hook to this guy. No light. Probably be easier if I could maybe tip this a little. I could have them backwards. We'll see. let's do that. So nothing. Nothing. I definitely want to test these lights to make sure that they work. If not, we have to replace them all. And there's a lot of them in there. Very strange. I think maybe a wire broke. Because these don't have a return path. Should give me a short. Oh, yeah, what am I thinking? I told you they're coated wires, which means they won't light up. So that's the orange. So, orange. Let's put on this side of the resistor, right there. There we go. So they're in bundles. They're not separated by color. So when I do this one, it turns on the reds, yellows, and oranges. Turn this one, it does the one side, and then this one does the other side. So it's segmented in 3 pie shapes, basically. That's 2 volts. I dropped it to 2 volts because at 2.2, the oranges were the wrong shade of orange, which means they're being overdriven and close to the burnout part. So just to show you again, leg 1. Let me do something else. Let me turn off the light. There's a big powered light above me. Probably makes it harder to see, so I'll do it again. Leg 1, leg 2, leg 3. And neither one of those 3 should turn on this guy down here. So I'm going to turn it so I can see through the glass. Clear off some of the dust. Leg 1, leg 2, leg 3. Good. So we know that all the uppers work. Now we need to see if we can get Frankie down there to light up. And to do that, I believe this wire here is going to be my ground. Right there. And oh, maybe that's the hot. I gotta turn the light on, I can't see. Alright, so the blues may not be functional. Which you can remove him from the bottom. I already did that, and I put some tape over it to hold him in so I can move this around. But this can't come out. You can see how he's moving in there. There's a hot glue on this, which might be causing my problem where I can't get a good connection. And then the blob chip that controls it is right there, and it's cracked and melted from the overpower. So, yeah. always always good. Yeah, I'm getting nothing from the lights on the bottom. So we'll probably have to replace those lights. Not a big deal. One thing about this is no longer going to be a 3-volt system. I don't have the transistors to make this 3 volts, and I also don't have the blob chip to know what chip they're using to time it. Most timer chips run between 6 and 12 volts. So this is going to be a 6 to 12 volt unit depending on which circuit works the best to handle the amount of current for this many LEDs. As you can see, there's quite a bundle in there, plus the one up here. And then, of course, I think there's 4 down here. So the next step is I'm going to move this off the bench, and we're going to build a lighting circuit. And then we're going to see if the lighting circuit will run all these LEDs, and then it'll be done. So this will be a more in-depth as well as technical one, but this will help you on this piece. And if you do have this piece and you've lost your power supply, 3 volts. Don't plug anything in stronger than 3 volts. It's the 56.54602 from Department 56 for the Snow Village Dr. Lunatics Laboratory. There you go, so you can kind of read it without the glare of the light. And just so you have the power consumption, in case you don't want to replace it with the OEM one, it is 3 volts DC, 300 milliamps, which is just under a 1/3 amp. So anything above 300 milliamps is fine. So if you get a 500 milliamp one, or a 600, or even a 1 amp or 1000 milliamp one, you're not going to hurt the unit. It's the voltage that's important on this. You don't want to go below 300 milliamps. And then it uses the standard 5mm barrel jack. The center is hot and the outer sleeve is negative, or as I say, hot and not. So you can replace this with OEM or aftermarket. So if you're just going around the house and you found you have a 3 volt DC power supply from an old toy, technically that would work if the barrel is the same and the output's the same and the milliamps are higher than 300. So let me move some stuff around here and get a breadboard, get some lights going. And we're going to work on a lighting circuit. So we can get this one and the other one fixed and get it sent back to its owner, and I can put mine back in my display. And again, I didn't fry mine. Mine was, I bought it cheap because somebody else plugged in 12 volts. So it happens. But I'm probably going to change the voltage anyway because I'm going to integrate it into mine where I can make my own power supplies. So it is what it is. So let's get this started. Be back in just a moment. Okay, we're back. This is the circuit. I was going to build another one, so I could put one in each house, but I'm short 1 resistor. So I was going to build the other one live with you. If I can find one, I'll still do it. At the moment, I'm 1 resistor short. So, as you can see, turn off the light here. I have 3 different LEDs, and you can see they're flashing in a pattern, which is what Dr. Lunatic's lab did. It flashed in a rotating pattern. This is a little bit slower, I believe, than the original. It's hard to tell from the videos that I watched to see the light pattern from the Department 56 piece. So it's pretty close. Now we just need to incorporate this into the house. And also, this is not 3 volts. This is 12. Most of these lighting circuits are between 6 and 9, or 6 and 12, sorry. But this is almost an exact duplicate of what's on that little circuit board. Turn the light back on. And I'm going to zoom in. Try and move this over without... So on that circuit board, where you saw the 3 transistors and the cluster of resistors, if you remember, where did I put there it is. So I'll bring it back in. 3 transistors, clusters of resistors, and a capacitor. So this uses 3 transistors, cluster of resistors. It's got 6, while this board has 4. And then this has 1 capacitor and this has 3. Because what this is doing is this is probably sharing amongst the 3 transistors right there. Well, this is all individual. So, but this is almost an exact replica of that, except that that's a little bit larger of a circuit. Also, it's a higher powered circuit due to the fact that the transistors, and they're different transistors. These are the same transistors I used in the Octo Squeeze. They're BC547s. This is their model. The capacitors are 50 volt, 100 microfarad capacitors. Those resistors, well, this one's off screen now, but the ones that are right next to the capacitor, those are 10k ohm or 10,000 ohms. And then these guys, which you can see that one there, which go up to the same bar, that are different color code, they are 560 ohms. So those are the components. You need 3 10Ks, 3 560s for resistors, 3 100 microfarad capacitors, 25 to 100 volt capacity, 3 BC547 transistors, solder, wire, so on and so forth. Oh, and then of course you need lights, because without the lights it doesn't do anything. There's no representation. So this is just on the breadboard for showing you how it works. Again, this is a much larger circuit. I mean, if I stuck it on a miniature board, it would be slightly larger than this, mainly because of those capacitors. You can see that little guy right there, little orange thing, it's kind of tan actually, is much smaller than those, because that's a ceramic capacitor. Those are electrolytic. Electrolytics are generally much larger, and they usually can handle higher temperatures. They don't really dissolve as fast, but they do explode. So, you know, there's trade-offs. So, now, let's see if we can put this in this. The only thing I might do differently is the blue LEDs that make the bottom flash. I don't know how much of a load balance difference there is, because if you watch the video, it shows all 3 of these, and on one of the 3 pi cycles, I guess I should zoom out so you can see what I'm pointing to. Again, wrong way. So on the pi cycle, where there's the 3 wedges, when one of the 3 wedges comes on, it lights up the blue. The reason the blue is not lighting up, as I think, is because that secondary board is blocking the power, because that's where the main fry is, because that's where the blob chip is. But we don't really need a blob chip. I don't understand why some of these come with them. You can see I can make the light pattern flash without a chip and without an integrated circuit on there. I don't know why. Just make it proprietary. I have no idea. But you can replicate some of these, like I showed you with the Octo Swing, without the important blob chip. Not all of them, some of them. So let's take this, stick it in here, and see if this cup does its thing. So I'm going to go turn on the big light so I can see better. Turn that off. The LEDs I used are the same forward voltage as these. So I didn't use a higher forward voltage LED or anything like that. I wanted to use the same as these, so I know that we have a relatively consistent power consumption. The only difference is I'm only using 3 LEDs and not 30 LEDs, like there. This circuit can almost indefinite length of LEDs, meaning you could have 666, which would be 18, and you could have 10, 10, 10, which would be 30. This circuit can handle up to a certain amperage draw, but this draws a 1/20th of an amp as it sits right now with those 3 LEDs. So. originally soldered the jumper wires on, these could get soldered directly to here. As you can see, there's 3 blues, 1, 2, 3, and then I have this guy over here, which is blue and yellow, which is the ground. 3 blues, 3 whites. The grounds are right here, and they're the part that's resisted. So the resistors on here would be the resistors on here. So this should be fine. I don't think I'm gonna need these. I will leave them on for testing, and if not, then I'll just disconnect them and then we'll test them again. And hopefully it doesn't blow all the LEDs, because that would be bad. So first things first, let's get rid of this circuit board. Here's the circuit board up closer. If it'll focus, probably not. But you can see the 3 transistors, 4 resistors, capacitor, and then they have jumpers. And the jumpers are over where another resistor is supposed to be. Those are jumpers. Those resistors are right here. So this actually does use a total of 7 resistors. And I think the 7th resistor, this one here, is for the power transfer to the board down there. So this circuit and this circuit are almost identical except for the capacitance. This is using 3 capacitors, this is using 1. This resistor is for the board that goes down here for the blue lights, and then the resistors that would go here, which are the resistors that are here, the 560 ohms, are right there. So it's almost an exact duplication, but it's a higher voltage because these are 8550S transistors, and these are BC547s. I had them, so that's why I used them. If I had this style, I would have done it this way. Probably run at a lower voltage. So I've got my soldering iron fired up, so we can work on all this. I can desolder those and solder these, and then we can test it in the piece. So while my soldering iron's warming up, I'm going to strip these wires back. And if I cannot find another resistor and do another circuit at the end of the video, I'll link to at least one on YouTube. This is a common lighting circuit, so I can link to one on YouTube. If you want to build one yourself, I can link to it so you can do it yourself. A lot of these circuits that they use are common. They just use blob chips to control them for some unknown reason. Alright, so now I'm tinning the wires. That. Those are off. I'm sorry if you hear that fan sound. I have a power supply that's running, and it's getting warm in here, so it keeps turning the fan on. Might just turn that power supply off. I don't need it at the moment. If you have helping hands, this would work great because it's hot. Transfers the heat really fast through the component. Also depends on your temperature, your soldering iron. Mine's set for 250C. Yours might not have an adjustable temperature setting, but that's what mine's set for. Trying to fix this. When I did it, the resistor came off. There we go. I think it's fixed now. Get that cool. Good, good, good. So the ground should just be able to, like, so I'm going to use the resistors at first just to see what happens. I'd rather them be dim or slow than instantly all burn out, because that sucks. Let me remove my jumper like that. So, technically, this should technically work. Technically. Let's make sure nothing desoldered real quick when I got that hot. Those are all good. Those are attached. Oh, yeah, that would be bad. The ground was... There we go. And let me turn off that other power supply. There we go. Okay, so this top rail, where the capacitors are facing at, is the hot rail, and the bottom rail is the negative. Plug my machine in. Okay, so no lights, and that's probably because of those resistors. So that's why I wanted to try it at first. Figure they might cause a problem, too much resistance. Resistors are off. And I'm going to twist all three of the grounds together. Like that. Itty bitty little piece of solder. Let's tin this without burning my fingers. Ooh, it's getting warm. All right, that should be good. It's attached. All right, Take two. No lights. The machine shows that we get power draw. So, alright. Let's drop this back down to 2.3 volts and just test the lights independently again. To ensure I don't create a circuit backwards through the mechanism, I'm going to desolder it and connect the grounds. So, lights all work. All the solder joints are still attached. So I don't know why this thing's not turning on. Bump up the volume here. Alright. Negatives, positives. Tree and tree. Those are disconnected. That's separate. Well, they do turn on, but they're really dim. So I think the resistors might be too high. I'm going to turn the lights off so you can see it. And one more light. And if you look, see? Just the reds are coming on, I believe. Yeah. The other ones are on, they're just super, super dim. So we have a power problem. Not power coming in, that's 12 volts. The power problem is going to be in the resistors. The resistor is probably too high of a load, so I'm going to have to adjust my resistance levels. This is why we test things. This circuit should have worked just fine because of the way it's designed. But I think the reason it's having an issue is even though they're all within the same voltage range, they're not all the same range. So the reds can come on as low as 1.9 volts and these run to 2.2, 2.3. The oranges are 2.1 to 2.3 and the yellows are like 2 to 2.2. That 0.1, 0.2 volts makes a big difference on LEDs. So circuit number one, test on the breadboard, works fine. In actuality, has a problem. So it's almost back to the drawing board. Now it's time to go back and adjust the resistors for the LEDs and change their resistance. So that way we get a little bit more juice to them and they start to rotate, hopefully, like they were doing on the breadboard. I'll turn the big light back on. So the 560 ohm resistor is probably too high. I probably need something around maybe 480, 500. So I gotta dig those out and try it. But so test number 1, failure. So I'm gonna reset this, and we're gonna do test number 2 once I find a little bit different value resistor, and we'll try it again. Return in just a moment. All right, I'm back. Took several attempts to get it to work. Ohm's law, for some reason, wasn't working the way it should have, because I don't know the exact milliamp draw of these LEDs. I only know their forward voltage. But boom, there we go. So if you're building the circuit, it's not 3 10K ohm resistors and 3 560 ohm resistors. It's 3 10K ohm resistors and 3 110 ohm resistors. And those have to be a higher wattage rating because they're going to get really warm. I know I burned my fingers on it the first time. So the circuit works, it's just the resistances are wrong for the quantity of LEDs because they're in different voltages. Because red, yellow, and orange. So 12 volts coming in. There's 12 volts. And there we go. They're all flashing. For some reason that one's dim. The rest of them are bright, but that one's dim. LED might be going bad. So this circuit will work. I'll have to build another one for the other piece, but we got the rotating lights. And it can get soldered directly to this and have a 12 volt try that again. It can be directly soldered to this and have a 12 volt input to work because it's running at 12.1 volts right now and it is pulling 0.3 amps. So this thing's going to run about a third of an amp when it's all said and done because they've still got to get the blue lights down here to flash. And this guy up here is not flashing. We'll turn the big light back on. So as far as the blue light goes, that's around Frank, and the dome light up here, I'm probably going to do what I did in the octo swing, so I'm not causing a balance issue on these lights, is I'm going to just solder a flashing LED in series and make them flash that way. So it's just that one LED is just dimmer than the rest. The rest of them are pretty bright. Reds are the brightest, of course, but it's also the angles. I'm just shadowing the light so I can check all of them as they rotate. Yeah. So I will see if I have another set of higher wattage LEDs, and I'll build a circuit for the other one. But let's finish this one up. So I need to solder the incoming power to that. The center hot should be the stripes, which we'll check. Because if they're not, that'll blow up. You can't reverse polarity on those capacitors. They don't like that. And then we'll get those lights flashing, and that light right there flashing. And we'll glue it all back up. And I can let the owner know that theirs was done, and I'll get mine done, and we'll call it good. So it's turned out to be a little bit of a process. It's a learning curve. It's a Ohm's law works, but you have to know certain things. And I was only guessing, and my numbers were off, of course. So soldering in here is horrible on the lungs. You need to have a well-ventilated area, and it's hard to do it in this little area. But there we go. Everything's lighting. Make sure they're all lighting. Now this, because it's all exposed, you don't want it touching anything inside. You can use a liquid electrical tape, or you can mask it off with, oh, I forgot the name of that cellophane tape. That's not packing tape, but stuff for electronics. Something to isolate the leads. There's not much in here that it can touch that can short out. If it's down low, where you drop this all the way to the bottom, like the original boards were, they're not coated and they didn't short out. This one has the blob chip as well. So there's 2 blob chips. You can see it right there. And I don't know if you see that point and that little dark spot in the point and the reflection of light. That's where the blob chip is cracked. Right. Where is it? Right there. That's from the wrong voltage going to it. So the transistors may still work. The resistors are probably still good. The blob chip failed. When the blob chip fails, you lose everything. So I'll probably keep these and test them, and if they're still good, I'll either use them for a house that just needs a new board. It wasn't overpowered, it just died, or I can just take out the existing components, or I'll just desolder them and put them in my buckets of parts. So at the moment, I'm going to set those off to the side. And I know these lights down here are blue from watching the videos on YouTube. These are resistors. I'm going to get them out of my way because I need to get to my LED buckets, which are underneath. The Octo Swing one, I said I only had white flashers, and then I found my other LED case, and I have other colored flashers. And I believe one of them is blue. So here's an LED tester that was made. You can also buy them pre-made. You don't have to buy them where they look janky like mine. That's blue. It's kind of hard to tell with the camera and stuff, but you see it's flashing? Yeah. So I can desolder or just add another one into there and they'll all flash. And this one's already blue, so it's not going to change the color palette that's inside of it. I forgot I had this other case because I didn't know where I put it, because I turned a couple of little model cars into police cars. They were already model police cars. They have red flashing, amber flashing, white flashing, and blue flashing lights. So I have white, amber, red, and blue that self-flash like that. So these are the original 560 ohm resistors. They're going to go back into the resistor case that I moved over there. So I'll put those out of the way. I'm going to turn this off so I can move it and not short it out. So I'm going to take this off. So like I said, I use duct tape to hold it on. Once I took the glue off of it. And like I said, if I remember right, all these lights on here are blue. So I could technically take that light there off, put the rest of them in series up inside, and they should all flash. Or I could just take all 3 of these lights and change them to those. will have to put a resistor on them, of course, because the voltage difference. I forgot the circuit board's still attached, the other circuit board. So I need to pull it back up to take that circuit board off. Now, this guy right here, which this blob chip is completely separated. So this took one hell of a hit from the power problem. Now we can test the colors. So I'm going to turn my meter on, or machine. I'm going to set it for 1.5 volts. Blue LEDs, depending on the type and the manufacturer, can run up to almost 6 volts, which I don't think this is that style because, of course, it's a 3-volt house. But let's check the color just to make sure. Well, we're at 3 volts and nothing's lighting up. So unless there's a voltage multiplier is what this chip was. That's where the power can come in and then it gets stepped up, but it doesn't look like it. These LEDs may just be bad. They may have been shorted out. Like I said, I believe they're blue from what I've seen online. Nothing. Just taking the solder off, so I have fresh wire just to make sure it's not a bad solder joint. And no lights. Just in case they reverse the wiring coloring code. Nothing. That's 3 volts on this one. That's 4 volts. That's what these are. These are 3 point something to 4 volt flashers. But, you know, let's just double check the lights as far as the color. So we're going to quickly pull up the YouTubes. And we're going to search for Dr. Lunatics Laboratory. There it is. We'll go full screen. Yeah, it might be hard to see, but that's flashing blue in there. I don't know, the flash pattern on here is about the same speed. So, yeah, that's why I thought it was blue. Trying to separate this one from the hot glue. We're just going to replace all the lights with new ones. Hopefully. These might be a little harder to get out. So we'll start with this big guy first. I don't think they used hot glue. There we go. Well, the LED itself doesn't look bad. I'm looking through the clear plastic with some magnifiers. So I am not sure why it doesn't work. It's probably just burned out. It probably got overpowered in the, I think it's called the anvil. The part that goes across the lights up, probably fried. Yeah, because that's 4 volts. That light should have come on dim and then burned out, but there's nothing. There's no resistance. So. Alright, we'll double check these one last time. Just to make sure, because those are going to be the hard ones. Because those are shoved up inside the thing. Yeah, we got no light. Alright. So there's a couple ways to do this. You can put 3 lights in here that are wired in parallel. Because they're flashers, you don't want to wire them in series. Or you just make one a flasher and then wire the other 2 in series and they'll flash accordingly. So there's 2 options on here. I've got to see how we get these lights out. Okay, good. They're just have a small itty bitty amount of glue on them. So for this guy, so I got a big chunk right here. There we go. That's the right size. You can see the whole fiber optic is lighting up. Kind of looks purple on camera, at least it does to me. It's blue. So, again, the choices are, if we put all these in, we could run individual wires like this all the way up to the incoming power with a resistor. Or we just make one of these the flasher, like this guy here, and then wire these in series, which means there's only 2 wires going up here versus 6. And in series, the 3 LEDs, the 2 blues that are non-flashers and the one that is, would have a forward voltage of close to 12 volts, so they may not need a resistor. It's usually a good idea to put one in there, but... And then, of course, you have choices, like you have the colored blue, or you can get a clear lens blue, which I'm out in this case, apparently. Let's check my other case. Pink, yellow, orange, blue. So I got clear ones there. The clear lensed LEDs are generally brighter than the colored lens LEDs. The colored lens LEDs, there's nothing wrong with them. So if you're making like a car tail light, let's say you're changing a car over to LED, you'd want to use a red colored lens because it's a red tail light. And if you're doing an orange for directional or something. And this is what I'm talking about when I say if you wire them in series or parallel. So let's just put these guys in. This is why the videos are so long, is because I try to go over everything. So you can do this at your house. Three. So that's parallel. Yeah. You can see that one's flashing and those two aren't. And that's at 2.7 volts. So if we bump it up to, let's say, 3, you can see those are now much brighter. You can see the one's flashing and that one, those two aren't. So if you did it in series, parallel means all the positives are on one side and all the negatives are on the other. So the incoming power is parallel to each other. In series, we would go hot to, so go hot, negative, and then off the negative would be the next hot. It's kind of like putting batteries in like an old radio or something, or where they're all in a row. Then that one's hot, and then we go negative, and then hot to negative, and then we go power out, power in. There we go, like that. And if I turn my machine back on at 3 volts, it's going to be off, because the forward voltage of all 3 of these now is about 9. So here's 4, 5, 6, there's a very small tinge of blue I can see, 7, 8.5, they turn on. And look, all 3 of them are flashing. So let's bring this up to just over 9 volts. This is 9.4. And this would be a parallel, or excuse me, a series circuit. So if I put the one flasher on the bottom and the 2 flashers in the fiber optic tubes, I only have to run 2 wires back in, not 6. But I have to run it at a higher voltage. So with this being a 12 volt unit, it'll be able to do it because I'm running 9.4 volts to power this. So I just need a resistor that drops it from 12, or it'll kind of handle the amperage from 12 to 9.4 or 9. This would be 9, there's 9 volts. And there's 9.5. And that's 10, which is probably as bright as you want to go, because now you're pushing the limits where you have these two can run. I'll tell you here in a second, because it's actually the nice thing about this company is they print them on the bag. So this has a forward voltage of 3.2 to 3.4. So 3.4 plus 3.4 is 6.8, and this other one can run up to 4 volts. So if I'm running it at the same, right now, each of these LEDs is drawing 3.333 volts each to make it the 10 volts that it's at. That is about as maximum as I can go before I start burning out the LEDs. And a matter of fact, at this 10 volt, I am getting bleed through, which I can see. The camera probably can't pick it up because of how bright LEDs are. But when this one turns off, these guys are still on very dim because there's bleeding through. It's not turning off 100% because we're running it at the maximum power. Maximum power might be great for a drag race where you're going from the start line to the end of a quarter mile and you want to get there instantly and be the winner. But when you're doing LEDs, this shortens their lifespan when you run them at max power. I'm not going to run them at min power. Min power is... you can barely see them flashing. They're super dim. So I plan to go pretty much in the middle. Good brightness, good power consumption, longer life. And I'm going to do them in series. So I'm going to put the 2 non-flashers in the tubes and the flasher on the bottom. So that way I can just glue the wire down to here and then run this wire off inside. So where there's not so many of these things inside this house. Since it's a 12 volt house, we have a few different options on how to do these things. And I can wire this dome piece, which is in here, into the same circuit. It'll flash. I'll have to adjust the resistor to compensate for it. This, I believe, is an orange one. Let's see, where is the dome light? It's this guy here. It has a resistor on it for 3 volts. We're not going to be using 3 volts, so let's get rid of this, and we'll, there. This blob chip It might be hard to see, but it is completely destroyed. It is peeled back and everything. And I said that's why this house doesn't work anymore, is because of the overpower. Now again, these are varnish coated wires, so I'm going to burn off a little bit of the varnish real quick. Like that. Now I don't know which way is positive and which way is negative, but my LED tester, I can plug it in, and either it will or it won't light up. Stay parallel. There we go. Nothing. Hopefully that one's not burned out. That would suck. Yeah, I'm not getting anything. Just to ensure that I have a good connection, I'm gonna scrape these real quick, just in case it didn't light it long enough. And one. Nothing. Nothing. Alright, so that guy's burned out too. So that means I need to heat the top up and replace that LED. Oh, wait. Hey, there it is. Just can't get a good connection. There we go, good connection. So good. So now let's mark which wire is which. So I'm going to take a red Sharpie here, and I'm going to paint this varnish red. Like that. Now let's put this into this circuit. So I need to remove that wire there, and then the hot goes into the negative of the other LED, then the negative goes into its own slot, and the only problem is that varnish, if it's not, there we go, yeah, the varnish is. With that, it requires 12 volts. So as you can see, it's flashing and it's pulling 12 volts. Yeah. So if I run a resistor on it with that one in series, it won't flash. I could put like a 1 ohm resistor on it for a spike, or a 2 ohm. I probably won't, because most of the power supplies I use are regulated power supplies, meaning that they're 12 volts and they stay at like 12 volts until you draw close to their amperage and then they drop. They're not always the cheapest power supplies. So I'll have to check my power supplies. Like the Octo Swing, the last set of 4 videos that I did, that one used, the power supply was 12 volts, but it was 12.15 free float, and it was a 5 amp power supply. Once you hit about 4.5 amps, it would drop below 12 volts. It's a regulated power supply. It's a very good power supply, but I wanted to make sure it stayed even because of all those chips I put in there and the different circuits to make that thing work. I wanted to ensure that the power supply stayed smooth since it had the voltage dropper using the USB charger, it had the timing circuit for the swings, and it had 3 different lighting circuits. So this will technically have 2. This guy here, which does 3 by itself, which is just 1 circuit, and then this setup here, which is 1 circuit using a flashing LED. Now we just got to glue it all together. In the interest of time, though, I'm not going to film that all. I'm sure you can just figure out how to glue the LEDs in, run the wires down, and solder them together. So they're soldered like this. And then I'm going to run them up and then connect them to the incoming power rails off of here, because all the power is going to come off of these 2 rails, the top and the bottom rail, hot and not. Like I said, it's just for time, because I know this section of the video we're already over 30 minutes. Like I said, some of this is really in depth, and these are why I said I'm going to have a couple of big videos coming out, is because of stuff like this where there's big circuits, lots of trials and errors and testing and non-testing and replacing burned out stuff, and then redoing it for a new voltage. But what's nice about this is, since the standard voltages for power supplies go up to 12 volts on average, if you get computer power supplies, they're much higher, or printer power supplies. If this gets a lower powered one, it just won't turn on. And if it gets a 12 volt one, it'll turn on. If it gets a really high one, it's going to smoke, just like the original. But luckily, most power supplies for these houses are between 3 and 12 volts. It has to be a DC power supply. If you do AC, you'll blow the capacitors up over here. And this LED won't like it. They should be able to handle it for a short time and not be a problem. This won't work. This will die, and so will those transistors. So if you do something like this, make sure that you are aware that you are converting not only the voltage, but possibly the direction of current from alternating to direct, because some of the Department 56, as a matter of fact, a lot of them are AC. This was a 3 volt DC house. It's now going to be a 12 volt DC house. So if you have a carousel or something that says AC on it, because a lot of them are, especially the houses that use the synchronous motors. If you change everything over, make sure that you have the correct flow of current. So anyhow, I'm going to pause it. I'm going to go ahead and pop those LEDs in and glue all the wires and run new wires up inside, solder them to the rails, and then we'll do a show what it looks like, and then I'll reassemble it and show you what it looks like in the dark. So be back in a few. There we go. It's back together. 12 volts. Camera only really picks up the red. You can see the orange and yellow. I don't know why it's just red, but cameras have a harder time picking up some LEDs. So 12 volt power supply. You can see the flashing lights. There we go. I'm going to turn on the light. So you can see the blue and the guy inside, Frank. So it's hooked up to 12 volts through my power supply. So I have to go find an AC to DC 12 volt adapter. Not a big deal. I got them, just not in here where I'm at. It's all back together. What I'm going to do is I'm just going to build another one for the other one that's bad. And I'll build that as a separate video in case you all want to watch the way I do it. And I'll still link to the other ones, or the other one that I saw. So there it is. The difference is when I change the resistor value down for these dome lights here, these are 1/8 watt resistors, which is what it calls for in the circuit. These are 2 watt resistors. So I changed it to 2 watts because the 1/8 watts were getting really hot. So just to give you an idea in size. Look at that. So from what I built, and then before I put it together, I swapped them out because I got my resistor, heavy duty resistor pack in. So when I build the next circuit, it's going to have the big fat resistors. So I'll link those below as well when I build the circuit and stuff. And I'll link them below on this one too. But it needed basically a couple of blue LEDs because all 3 of those were bad. And then building a circuit, which was 3 transistors, 6 resistors, and 3 capacitors. The lights in the front, I got the one blue flasher wired in series with the other 2, the blues, and this orange, so they all flash, just like you see. And a little easier to see. I ran all new wiring, because I did it in series, on the back side of Frank, glued it, ran it up inside here, soldered everything together. There's no resistor on these, because this is at 12 right now, it's at 12 volts, and it can actually pull, you can go up to about 14 with this guy in the circuit. So if I put any resistor on it, it makes it really dim. But it is running at 12.1 volts and it is pulling 0.33 amps. That's 330 milliamps, or a third of an amp, a little over. So, yeah, third of an amp. So this is a little bit more high powered than what it was before. The original one, which was 3 volts, was also pulling 300 milliamps. So this circuit's pulling 330. So this 12 volt circuit's pulling a hair more power. And it's probably because I'm using a high powered blue. These lights are all original, but these blue lights have a higher forward voltage. As I showed you earlier in the video, they can run 4 volts, while the original blue lights that were in here only ran at 3. So with these running at a higher voltage, they're going to pull a little bit more power. So that's why it's just a little bit stronger. But it's bouncing between 0.31 and 0.33, because depending on how the flash is, because one slice of the pie has more LEDs than the other 2 slices, which I think is stupid. They should be balanced. But there we go. It's all set. I got a glue string on here I want to get rid of. There we go. So dome's hot glued back on. I didn't resin glue it or hard glue it like a lot of them are, just in case it has to be taken apart to fix anything inside again. Frank's glued back in the bottom with hot glue as well. Same reason. If it has to come back out, we'll want to sit there and try and chip away at it for an hour. But yeah, there you go. 4 LEDs, 6 resistors, 3 capacitors, 3 transistors, some wire, solder, hot glue, patience, and trial and error, as you saw. So hopefully this helps if you have this piece or something similar that just has lights that aren't working right and the rotation patterns are bad or what have you. Here's the ability to make a new circuit and repair this piece, because this piece for some reason seems to be the one that gets fried all the time. So I'm going to get a 12 volt power supply, put it back in its package and ship it back to the owner, which I've been in contact with, and let them know that it's got a new power supply. I am going to write on the bottom, like I do on all the ones that change voltage, 12 volts DC. So other than that, we're all done. So thanks for sticking around if you did to see the conclusion of this piece. So this is Dr. Lunatics Laboratory from Department 56, just a lit piece with flashing lights. So, till the next repair, thanks for watching.